FLASHForward is one of the few experiments worldwide that uses high-energy particle beams to power a special kind of accelerator called a plasma accelerator. FLASHForward is a team effort combining experts from different areas of physics and engineering. The research group, consisting of approximately 20 people, is located at DAISY, a scientific research center based in Hamburg. Besides FLASHForward, multiple other conventional and plasma accelerator research groups can be found on the campus. But what is it exactly that FLASHForward does? To what extent does a plasma accelerator differ from the accelerators running today, like the LHC at CERN? And why is plasma accelerator research relevant? Let's have a closer look into the limitations of big particle accelerators compared to plasma accelerators. Particle accelerators are advanced instruments used in a wide range of research topics. On the one hand, accelerated electron beams can be used to create ultra-bright X-ray beams that are used to study materials on the molecular level. On the other hand, colliding particles allows researchers to study physics on the subatomic level. In conventional machines, the particles are accelerated by electric field waves confined within metallic cavities. However, these fields are limited by the electric breakdown of the metal cavities. This limitation necessitates increasingly large and complex devices to achieve higher energy levels, leading to substantial increases in both the physical size and cost of these facilities. This limit may be overcome by plasma accelerators. Instead of sustaining fields in metallic cavities with vacuum inside, the electric fields are created in a capillary filled with plasma. But what exactly is plasma? Plasma is the fourth state of matter, formed from ionized atoms. It is created when a gas, or vaporized matter, is heated to very high temperatures so that the atoms lose some or all of their electrons. This creates a mix of free electrons and positively charged ions. At FLASHForward, argon gas is often used to produce a plasma. It is created when argon gas is flowing through a tube made of transparent sapphire, and a short, powerful electric current pulse discharges the gas into plasma. Let's have a look at how acceleration in plasma actually happens. The process begins with the arrival of an electron bunch, called the driver beam, into the plasma. This driver is an extremely dense and fast-moving packet of electrons. As the driver propagates through the plasma, the negative charge of its electrons continuously repels the free plasma electrons. This strong repulsion forces the plasma electrons to move radially away from the driver. Meanwhile, the positive charge of the stationary ions pull these electrons back. This electron distribution forms a wave, or wake field. The charge separation in this wake field creates a very strong electric field. If a second bunch of electrons, called the witness bunch, is correctly placed within this wake field, it can be very rapidly accelerated to close to the speed of light, which is the main goal of plasma wake field acceleration. The driver drives the wake forward, meaning at its back, the displaced electrons are attracted back towards the ions due to their opposite charges. As a result, the witness particles are accelerated forward by the intense electric fields within the wake. While FLASHForward only focuses on electron beam-driven acceleration, experiments with laser pulses are performed at DAISY as well. In recent years, FLASHForward has been able to achieve multiple breakthroughs in plasma acceleration, especially when it comes to optimizing the acceleration process and improving its efficiency. Some of these major accomplishments refer to the quality of the witness beam. The quality has reached a desirable level when the dispersion of the bunch's electrons, as well as the dispersion of its energy, is reduced. The spread in space can be avoided when the witness is well aligned behind the driver's path, whereas the energy spread is avoided by shaping the witness correctly. While a high-quality witness beam is more useful when it comes to implementing the process into advanced applications, for example generating X-rays. Another milestone that FLASHForward accomplished was measuring the plasma's recovery time. Unfortunately, the plasma wakes, which drive the acceleration, quickly collapse after a single use. The plasma then needs time to recover before the next particle bunch can be sent. The researchers observed that the plasma returned to its initial state after about 63 nanoseconds for the specific experimental settings in the argon plasma. This suggests that a plasma could accelerate electron bunches at a peak rate of about 10 million bunches per second, although the number of consecutive bunches that this can be done for is a matter of ongoing research. Since the plasma capillary at FLASHForward has a length of circa 50 millimeters and results in an acceleration by about 50 MeV, plasma-based accelerators can accelerate to higher energies and shorter lengths. Potentially, this makes them a more affordable alternative for upcoming accelerators. For the future, FLASHForward plans to perform particle acceleration in even longer plasma capillaries and increase the energy gain while preserving the high witness quality and the efficiency of the acceleration. There are still many challenges to overcome. However, the experiments operated at FLASHForward show that plasma wakefield accelerators can potentially meet the demanding requirements for future applications. This paves the way for groundbreaking advancements in accelerator technology, benefiting research in particle physics.